Welcome to This Explainer. We're diving straight into how a totally groundbreaking AI system is solving a massive, literally mind-bending problem in deep space exploration. Imagine staring out into the vastness of the night sky, trying to find something completely invisible to the naked eye. Well, that's exactly the challenge astronomers are facing every single day.
So, think about this. How do you find a planet hidden in the blinding glare of a distant star? That's the ultimate needle in a haystack dilemma of modern astronomy. We can't usually see exoplanets directly through a telescope because the stars they orbit are just ridiculously bright. Instead, astronomers have to look for tiny, almost imperceptible dips in starlight. These slight dimmings happen when a planet crosses right in front of its host star. But spotting these minute drops in brightness across millions of glowing stars in the cosmos, it's incredibly tough. Okay, let's take a look at the incredible, extreme planets we're actually trying to find here. Picture an ultra-short period planet, a massive world tightly orbiting its fiery star, enveloped in a wild, dynamic dance of cosmic forces. This isn't science fiction, you know. This is exactly the kind of actual, extreme target that modern astronomers are hunting for in the depths of space. So let's jump right into Section 1, hunting for hidden worlds, and the sheer data overload we're up against. To find these hidden worlds, scientists rely on NASA's TESS mission, which continuously scans the sky for those slight dips in starlight we just talked about. But doing this on a cosmic scale creates a massive hurdle. To give you a sense of scale, in just its first 4 years alone, TESS gathered detailed observations from over 2.2 million individual stars. 2.2 million? It's an overwhelming data overload that's practically impossible for human astronomers to manually process, filter, and analyze all by themselves. And you know, the universe is full of astrophysical imposters, things like eclipsing binary stars, where two stars orbit each other and perfectly mimic the dimming signal of a planet. To overcome this giant mountain of data and false signals, University of Warwick astronomers unleashed a powerful new solution, an AI named Raven. Raven is designed to detect these signals, vet them using machine learning, and statistically validate the true planets. Moving on to Section 2, let's meet Raven the AI, essentially our cosmic detective. Raven really isn't just a simple algorithm. It's a highly sophisticated automated pipeline. Think of it as a highly trained detective with a 3-step workflow. First, it tirelessly scans those millions of stars for tiny brightness drops. Actually, scratch that. Let's call them what they are: anomalies. Second, it actively filters out the false signals, like tricky binary stars or just random instrument noise, using AI trained on highly realistic simulations. And finally, step 3, it statistically confirms the strongest candidates. The real game changer here is that Raven handles this entire complex process in one seamless, continuous go. Dr. Andreas Hadjigeorgiou, the lead developer of this pipeline, hit the nail on the head. He said, "We trained machine learning models to identify patterns in the data that can tell us the type of event we have detected, something that AI models excel at." And that's absolutely crucial. Raven's real superpower comes from this training. It was fed hundreds of thousands of meticulously simulated events, so it instinctively knows exactly how to spot the fakes. Which brings us to Section 3, rare and extreme planets, and the amazing loot Raven actually uncovered. So, what did this AI detective actually find during its investigation? Well, the results were just phenomenal. Using this new pipeline, researchers were able to definitively validate 1,118 new planets. Out of those 118, 31 are brand new, never-before-identified worlds. But wait, it doesn't stop there. Raven also vetted over 2,000 high-quality planet candidates, with nearly 1,000 of them being entirely new discoveries that are now primed and ready for future study. Now, what's truly fascinating is the sheer extremity of the worlds Raven found. For instance, the AI identified a category known as ultra-short period planets. These are extreme worlds that orbit dangerously close to their host stars, so close, in fact, that they complete a full orbit, a whole entire year, in less than 24 hours. Can you even imagine that? You would literally be celebrating a birthday every single day. Raven also uncovered planets lurking in what astronomers call the Neptunian Desert. This is a mysterious region close to stars where very few planets are expected to exist, at least based on our current scientific theories. Yet, there they were. The AI found them hiding out there, alongside tightly packed multi-planet systems, including completely unknown pairs of planets orbiting the exact same star. All right, on to Section 4, the cosmic census, where we map out the broader demographics of these findings.
Because Raven's process is entirely objective and the dataset is so carefully validated, astronomers aren't just looking at individual planets anymore. They can finally map out broader demographics across the galaxy. This demographic mapping shows us something really cool. About 9 to 10% of Sun-like stars host a close-in planet. This lines up beautifully with older data from the Kepler mission, but thanks to AI, researchers have reduced the uncertainties in these numbers by up to a factor of 10. That gives us a much, much more precise picture. And for the very first time, researchers were able to put a precise number on just how empty that mysterious Neptunian desert really is. They found that these rare desert-dwelling planets appear around a mere 0.08% of Sun-like stars. These measurements definitively prove that the TESS mission, now supercharged by AI, can match and in some cases totally surpass the old Kepler mission for studying planetary populations. Now for our final section, Section 5, a new era of discovery and how we're finally correcting hidden biases. Beyond just the raw numbers, Raven really represents a massive leap forward. By evaluating which types of planets are harder to detect in the data, it actively corrects for hidden observational biases. Because AI is fundamentally transforming these massive datasets into clean, reliable discoveries, the research team has actually released interactive catalogs for public use. This allows the entire global astronomical community to dive in, identify the absolute best targets for ground-based telescopes, and perfectly prepares us for upcoming next-generation missions. And that brings us to a final, pretty provocative thought. With AI like Raven now objectively mapping the stars, correcting our human biases, and producing these interactive catalogs to guide incredible upcoming missions like ESA's Plato Space Telescope, what bizarre and extreme worlds are we gonna discover next? When the universe presents us with an infinitely massive haystack, artificial intelligence might just be the ultimate magnet. Thanks so much for joining me for this explainer. Keep wondering, and as always, keep looking up.